Just 40 light-years away sits a dim red dwarf star called TRAPPIST-1. It is orbited by 7 rocky Earth-sized planets. This configuration makes the system a unique laboratory. With 7 similar targets in one place, astronomers can compare how different distances from the same star affect a planet's habitability. But orbiting a red dwarf has severe risks. These volatile stars frequently unleash massive solar flares, carrying enough energy to strip a planet's atmosphere. Before they settle down, they go through a chaotic, highly energetic juvenile phase that lasts for billions of years. During this extended youth, red dwarfs release frequent, massive solar flares. These eruptions act like a cosmic blowtorch. If a planet starts forming an atmosphere, intense radiation can strip those gases away entirely, leaving behind nothing but a barren, irradiated rock. Top of the intense radiation, the planets here orbit so closely to their star that they are tidally locked. One hemisphere faces a permanent day, while the dark side is plunged into an eternal, freezing night. To determine if these worlds are sterile rocks or thriving environments, astronomers have to look for a protective layer of gas wrapped around them. Until recently, analyzing those invisible atmospheres across interstellar space was practically impossible. That changed with the launch of the James Webb Space Telescope, an instrument sensitive enough to read the chemistry of these distant worlds. In transmission spectroscopy, as a planet passes its star, starlight filters through the atmosphere. The telescope captures this light, breaking it into a spectrum. Missing color bands act as a chemical barcode. Specific molecular bonds absorb specific wavelengths, revealing exactly which gases are present. Armed with this method, researchers are systematically analyzing the TRAPPIST-1 system, identifying which planets are barren and which require a closer look. The investigation starts close to the star, with the 2 innermost planets, TRAPPIST-1b and 1c. For 1b, the Webb telescope recorded surface temperatures reaching 227 degrees Celsius. That leaves the middle section of the system. Planet 1d sits right on the inner edge of the habitable zone, where water could pool. But Webb has detected no traces of an Earth-like atmosphere there either. That heat is high enough to rule out a thick, Venus-like atmosphere. TRAPPIST-1c was a surprise, the coolest rocky exoplanet categorized by thermal readings. It formed without much water, existing today as a barren, dry rock. These readings suggest the inner zone is sterile, forcing the search for habitable conditions further out into the system. That brings us into the middle region, starting with TRAPPIST-1f. This chart shows the potential composition of a steam world. If 1f is 20% water by mass, its proximity to the star could trigger a greenhouse effect, boiling that water into a high-pressure gas. Just beyond that is TRAPPIST-1g. Sitting on the outer edge of the habitable zone, the balance required for liquid water is much harder to maintain. Finally, we reach the furthest planet, 1h. With low gravity and a significant distance from the star's heat, it is likely a frozen wasteland. By identifying the likely fire, steam, and ice worlds, the data leaves us with one prime candidate sitting in the center of the habitable zone. That candidate is TRAPPIST-1e. It receives about 2/3 the energy Earth gets from the Sun, and initial observations have already ruled out a dense carbon dioxide atmosphere. This model shows a methane reverse greenhouse effect. High methane levels absorb the star's near-infrared energy, bouncing it back into space. Because TRAPPIST-1e is tidally locked, this allows liquid water to pool along the terminator line, the permanent twilight separating day and night. These conditions would mirror Charles Darwin's warm little pond hypothesis, providing a stable environment where early biology could potentially begin. Even with one side in a freeze and the other in daylight, a planet with this specific chemistry could sustain a life-supporting ring. There is an alternative theory that doesn't rely on the surface at all. TRAPPIST-1e might be an icy world hiding a liquid ocean deep beneath its crust. This comes from a process called tidal heating. TRAPPIST-1e doesn't travel in a perfect circle. Because of its slightly eccentric orbit, the star's gravitational pull constantly changes, causing the planet to be physically squeezed and stretched as it moves. This generates immense internal friction, keeping the core molten. A churning, molten interior is exactly what a planet needs to generate a strong magnetic field. By deflecting the worst solar flares, the physical torment stretching its crust might be the exact mechanism shielding its atmosphere from destruction. On an elliptical orbit, the varying gravitational pull from the star acts like a vice, stretching and compressing the planet. This internal friction generates core heat, powering volcanoes and creating a magnetic field that deflects solar flares. We see this mechanism on Europa in our solar system, creating deep-sea vents, providing both the heat and minerals needed for life to form. Whether biology exists in a twilight pond on the surface or near a volcanic vent underground, 1E appears to have the necessary energy sources to sustain it. We have not yet detected a definitive signature of life, but for the first time, we have the technological capability to observe and analyze the best possible targets in the galaxy. As the Webb telescope continues to decode these alien atmospheres, the search for life is shifting from theoretical models to direct observation. For the first time, the data is within our reach.